Okay, so this is the syllabus. I tried to make this semester as mentally easy as possible. Okay, not a lot of variety and assignments and things for you to worry about. We're going to have weekly homework quizzes, and then I think 3 exams. So an exam on the sort of the analytical calculus piece in quantum mechanics math and applications to 3D, an exam on the group theory and calculations with Gaussian folded into that, and then the last third, an exam on spectral simulation and deconvolution and so on. So there'll be 3 exams. Each of those is 20% of your grade. So that adds up to 60% of your grade. And then every week, these quizzes, which are meant to just tell you what I think is important, right? So if you study those quizzes, you'll do pretty well on the exams. Okay. So that's pretty straightforward. 40% for the homework assignments, 60% for the examinations. In-class participation, I just have listed as required. There are no points associated with it, but if you disappear, I'll check roll. If you disappear for a long period of time, I'll check in on you, make sure everything's going okay. If any of us get COVID, then I'm recording the lectures. You can watch them from home. Just make sure that I know that you have, or any other kind of illness or problem. Let me know. If I get COVID, we'll probably just do it remotely. Okay, I can just teach from home. If I'm incapable of teaching because I'm sick, really sick, then I've got a lot of videos that I can substitute. So we'll keep the class going no matter what, and we'll have a great semester. So after you're done with this course, these enabling objectives, you'll be able to demonstrate the competence in mathematics associated with quantum theory, interpret spectra through the lens of symmetry. You'll be able to sort of use symmetry-based arguments for interpreting data, and then you'll be able to create spectral simulations using Gaussian or other computational packages in Excel. The main thing is communication. So if you're having troubles, tell me soon. Okay, I know a lot of folks are shy and don't want to talk to me unless, if you're worried, it's like, I don't want to ask him this question because he's going to think I'm stupid. Okay, that's not a problem. Ask anyway. Okay, I don't assume those things. I just answer your question. Okay, so this is not something you should worry about. Okay. The quizzes are straightforward. Just download the PDF. You can work on your own time. Y'all can work together as long as you do your own work. Like you don't want to, and this, y'all are grad students, but if someone helps you with a problem, it's not about the answer. It's about knowing why it's right. And so if they don't know why it's right, then it's wrong. Now, I can only check the answers, okay? So you're the one that has to check whether you know it or not, okay? So y'all can work together. I encourage it because it really is good. Sometimes you get stuck and you don't know if it's a wall or a speed bump. And if it's a speed bump, your neighbor can help you get over it. But if it's a wall, then you both have reached a problem, and then you come to me and say, what do you mean by this problem? I don't get it. It's best if you ask that question in class because everybody probably has the same question. But if homework's, let's decide when do you guys as a group want homework to be due?
I like Wednesdays.
Like it's always going to be like at the end of the night, like 11:59 on some day, because that's.
What do you assign homework?
Well, it will depend. Whenever y'all pick the deadline, then that'll help me adjust when it's rolled out.
You get the same week that you normally give. Like say.
Yeah, you get the whole week. Yeah.
Sunday, you normally get one day, like for our class last
Yeah.
year.
Yeah. So.
Okay. And it's not the 10 pages, right?
No, this is not the 10 pages. This is just you pull down a quiz that has multiple choice and some worked problems and some things like that, and then you go on and you go online. Yeah, very similar to forensics. Then you go online and you enter your answers and you get a couple of attempts in case you mess something up. So it's really just when do you want those answers to be due online. I write the first week. This week I have it like Saturday night at 11:59. Okay.
Doesn't matter to me.
Doesn't matter to you? Okay.
Nothing.
You said Wednesday. Are you? I mean,
I just like it so that way, like, say if we forget about it, we still have a couple of days to do it after we see everybody.
yeah. Okay. So midweek is kind of your target.
Wednesday or Thursday?
I'll second Wednesday.
Wednesday night. Is that okay with everybody? Okay, so I'll start thinking about making things roll out. Like I'll roll them out on. I'll probably roll out the next assignment on a Wednesday, but I don't. I like. Let's see. How do I want to do this? Yeah. So I'll just have them do. They're in weekly folders, so I don't think you're going to have any problems with like overlapping things that are. It'll satisfy the confusion that I used to have. This was a problem, but now it's not a problem. So each week we'll have a folder. That's the structure of our course. So you have a weekly folder, and in that folder is everything you need to do for that week, including like when it's like a week or so out from the test. I'll say, you need to start summarizing things and studying for that test. It's not in this week's folder, but it's coming up, And so, can you close the door, please? Okay. Now, in terms of getting grades back to you quickly, I like for you to do like part of the test with a Scantron. So this green Scantron form that, it's like got 50 questions on it. But we will have maybe 25 questions. You answer A, B, C, or D, and you can fill that out. Then I can grade those really quickly. And then there'll be some written parts too, where then I have to grade the handwork. And that takes me a little longer, but if I can quickly run those Scantrons, then that'll be nice. And so that's so bring a pencil, a calculator, eraser, and a Scantron to the exam. Okay. At this point, I'm not doing note cards for a graduate course, so you gotta bring your knowledge, have it in your head. When we do I would like for some of the exam problems, since we don't have projects in this course, I may have like a take-home problem that you can prepare before the exam. Like, if it's a Gaussian calculation and it produces a simulated spectrum, then that might be a take-home problem. That's a bigger thing than just a weekly homework problem. And so I want to put that into the exam points. Because the exam points, there's a lot of points there. And so if we have like a longer assignment, I may make that part of the exam. Okay. And so then there'll just be a submission link on Blackboard. But I'll give you those informations as we go. Now, if you're doing any writing associated with that, the definition of plagiarism is 10 consecutive words from another source that has not been cited. Okay. And if it's 10 or more, it needs to be in quotes. So don't fall into that trap. Last time we had someone fall into that trap, they had used whole blocks of text from a website, in one of their papers. And so whenever we turn in something that's written, it will go in through this software that scans everything and compares it to all these other papers and websites, and it will flag plagiarism and say, wow, this is from this particular source. Now, sometimes like if you quote it, like if you have a paragraph from a web page that you find, it says it so well, you can't say it any better, right? And so you grab that paragraph and it's in quotes. Now, this software will pick that up, but if you cite it and you quote it, then it's okay. It's not plagiarism. Okay. So it's not that you can't use other sources. You have to cite them and you have to quote them if you're going to use them. Because otherwise you're claiming that they're your ideas. And so that's the difference. Okay, so the syllabus is on Blackboard. The rest is probably self-explanatory. If it's not, then just get with me and I can answer your questions. Okay. So what I'd like to do quickly in the time we have remaining is to give you a bit of history on quantum mechanics. And so let's think about this strange concept that nature is quantized. Do you know what I mean by quantized?
Discrete parts.
Discrete. Yeah, this word discrete and quantized are synonymous. Think of the stairs. versus a ramp. So if you have a ramp, you can stand anywhere on that ramp and have essentially an infinitely variable potential energy. But if you're on stairs, you're either on step 1, step 2, step 3. And so we've discovered that nature is quantized. That's strange. Why is nature quantized? Why can't an electron have any energy when it's attached to a nucleus? Have you really thought about it? Yeah, it's strange, isn't it? So let's go through some history. So before Einstein, before Schrodinger, before Planck and Boltzmann, even before Newton, we have René Descartes, who wrote this idea. He was trying to figure out, how can we find the truth? And so he's the one that questioned everything all the way down to his own mind. And then he thought, if I'm thinking, if I'm questioning, there must be an I. And so that's where this word cogito ergo sum, I think, therefore I am, came from. So he backed all the way back, and the only thing he could be sure of is that he existed. Now, strangely, he couldn't be sure that anything else existed, but he could be sure that he existed. And then building his philosophy back up from that, he said, okay, we need rules for the direction of the mind. And so rule number 4 was there needs to be a method for finding out the truth. And then he was discussing this method and what was the method for finding out the truth. One of the useful methods that he found was mathematics. And so mathematics didn't begin with him. It was earlier than that. But still, he was the one that tied mathematics to truth because it's objective. If you do the math, I do the math, we get the same result. Okay, it's not culturally related. It's not related to any of these other things. It's a way to find independent results. And so he says, and also thinking about the mind, he says, this idea of math is a useful mode of thought. He thought of it like a germ, like this little particle that got transferred from person to person. And so let's trace this germ of useful thought, mathematics. And he wrote geometry. So he was studying angles and triangles and circles and so on. And he wrote this book, Geometry. And guess who picked that germ up next? Newton. So it was Descartes' book. And Descartes, that word cart, you've heard of Cartesian coordinates? That's where it came from, this book, Geometry. So it's old. This concept of a Cartesian frame, X, Y, Z, is very old. And Newton saw this and he said, I think math is a great way to study nature. And so, the apple falls on Newton's head. He thinks about gravity. He uses math to describe it. And so then we have Newton's laws of gravitation and so on. And so this germ of useful mode of thinking, math, jumped from Descartes to Newton. It was so successful that they could predict the future. Now, did you know you can predict the future? You ever do in physics the cannonball problem? The cannonball leaves the muzzle of the cannon at a certain velocity, so many meters per second at such and such angle. And you're asked in class, where will it land? You're predicting the future because the ball had just left the cannon and now it's going to go into the future and land in a certain spot, and you can predict the future. This was so successful, it led to the Industrial Revolution. Steam power, everything was based upon Newtonian physics and calculus. It was so successful. This is a British poet. And I don't know if you've heard the phrase in Genesis, the Christian Bible, that in the beginning God said, let there be light. You know this, let there be light? Okay, this is a British poet, and he said, nature and nature's laws lay hid in night. And God said, let Newton be, and all was light. So this is how much they valued Newtonian calculus and Newtonian physics. That God didn't need to create light, he just needed to create Newton, and everything else was illuminated. So it's kind of funny to think, but I'm trying to get the point across of how much value was placed in Newtonian physics and how earth-shattering it was when Newtonian physics couldn't explain things. Because it couldn't explain black-body radiation. It couldn't explain the atomic spectrum of hydrogen, the simplest atom on the periodic table. It couldn't explain our photo detectors, our cameras. These are quantum devices, and Newtonian physics can't explain them. So there were some problems that they were discovering with Newtonian physics, which is a tough sell because Newtonian physics was so successful. So this is sort of following this thinking. So math went from Descartes to Newton, which passed it on to Boltzmann in the 1700s. And Boltzmann was solving the equilibrium of gases. So the kinetic theory of gases, you study that in the freshman course way back when, your PChem course too. But one thing that's not typically pointed out in those courses is that in order to solve this really difficult problem of the gas particles in a box, think of how many velocities they have. And he's trying to figure out the entropy of the box. So he needs to know what the distribution of velocities is in this box. And he says it's nearly infinite. So Boltzmann said in his paper, to simplify the math, I'm going to treat them as discrete velocities. So he quantized things. And so he introduced this idea of discrete velocities. Now, he said in his paper, this is just for mathematical reasons. I'm not saying that gases can only have certain velocities, but it simplifies the math. And so Max Planck, when he was working with blackbody radiation, used Boltzmann's distribution, the discrete distribution. And so that's where quantum effects came into play in Planck. Planck is normally given the credit for this idea of quantized nature, and Planck's constant was called the elementary quantum of action, but it was the math of Boltzmann that he used. Yeah. So then Heisenberg also developed math related to quantum mechanics, and then it was this idea, this mathematical idea, combined with de Broglie. That's how you say his name. It looks like de Broglie. It's called de Broglie. He brought in the math, and he also loved music. And he said, well, this strings on a violin or on a guitar have discrete frequencies, depending upon the tension, depending upon the mass of the spring, depending upon the length of the string. They have standing waves, and maybe electrons are standing waves. So he introduced this idea in his thesis. So this idea of quantum mechanics and wave mechanics, specifically wave mechanics, was in a thesis. Isn't that cool? Y'all are about to write a thesis. Who knows where it'll go? Yeah, right. And so then Einstein read his thesis and said, yeah, that's not a bad idea. And he told Schrodinger, you need to look at this guy's thesis. And so then Schrodinger looked at de Broglie's thesis and took his idea of a standing wave and developed wave mechanics. And so that's where the word mechanics came in. So just like we had Newtonian mechanics, cannonballs, we now have wave mechanics. And it's quantized energy levels. So we use the word quantum and mechanics together, but it's really the mechanics of waves, how waves behave, that explain the hydrogen atom, that explain the blackbody radiation, that explains quantum devices like our detectors and our cameras and our light-emitting diodes. So let's go through those problems. The Rayleigh and Jeans tried to fit the data for a blackbody radiator. So if you look at this is wavelength. So this is the blue part of the spectrum. Oops, I'm missing an L. And this is red at 700. So this is the visible part of the spectrum. And so this object is very hot. I think it's like 60 or 70,000 Kelvin. And so this would be bright bluish white. We would have all of the wavelengths of light emitted by this object. The strange thing about blackbody radiation is it doesn't depend upon the material. It seemed to depend only upon the temperature. If you'll notice up here in Rayleigh-Jeans law, which matched the data down here at long wavelengths, the material's not in here. It's just the wavelength dependence upon the emission. So this is the amount of energy per wavelength, essentially. So joules per meter. It's related to Boltzmann's constant, the temperature, and the wavelength. There's no molar mass. There's nothing that identifies the material. It's kind of strange. Stainless steel, copper, aluminum, all would have the same spectrum in this blackbody radiation. Now you can't really get wood that hot and get it to glow like you do metal, and so. But as far as the metals, all the different metals, it didn't matter what kind of metal it was, or carbon. It doesn't even have to be a metal. Like graphite rod will give you the same spectrum. The problem was that the Rayleigh-Jeans law went to infinity, but the data went back down to 0. And so the difference between infinity and 0 is enormous. And so this was called the UV catastrophe, because over here in the UV region, the emission went back down to 0. And it was Planck that solved this problem by using Boltzmann's distribution. Right here is Boltzmann's distribution. And he introduced this H. This H right there is Planck's constant. And we see that, I mean, all objects that are above absolute 0 emit light, and they're, like here's a guy with his arm in a plastic sack, and you can see his arm through the sack if you look in the infrared. Okay. And so this is Planck's struggle with quantized energies. He said using Boltzmann's distribution, his quantized math was an act of desperation. And he knew that the problem was fundamental, and he knew he had an answer that would fix the problem, but it would suggest that nature was quantized. And he was very uncomfortable with that, as was everybody. So he came up with this elementary quantum of action, and then that was allowed to explain, or that explained the photoelectron emission problem. So this problem was unexplainable too. The kinetic energy of electrons that emit off of a metal surface with light as a function of that frequency. So over here, this is UV, visible, IR. If you get down into the IR, the electrons stop coming off of this surface. Get into the visible, get into the UV. So this light is hitting the surface and electrons are coming off in a vacuum. You can detect them. And notice how the energy, the kinetic energy of the electron is a function of the frequency, and it's linear. What's the slope? And so and again, it didn't matter which metal it was. So you hit it with light, you calculate the frequency of the light, and then you can measure the kinetic energy of the electron, and it's a linear relationship. And naturally, if you see in any of your scientific data a linear relationship, what are you going to do? You're going to solve for the slope. So Einstein solved for the slope, and what was it? It was Planck's constant. So here was a second confirmation that Planck's constant had some fundamental role to play in nature. So Planck used his constant to solve the blackbody radiator. Einstein used it to solve the photoelectric effect, the slope of kinetic energy related to frequency, and that's what Einstein got his Nobel Prize for. Seems like a simple thing. He fit an equation to a line and discovered that the slope was Planck's constant and got a Nobel Prize. I know, man. Don't you wish it was that easy now? And I'm sure there was more details, but still, it's pretty amazing to think. The real Nobel Prize was explaining that this may be, leading to quantized nature. This is a dramatic change from Newtonian physics, where something can have any energy. Now, this is well described that a photon of light with a certain energy hits a single electron, and that single electron comes out with a certain amount of energy, and so this definitely supported the idea that light was a particle, right? Because think about it, you got an electron swimming around on the surface of a metal. How does a wave of light that's distributed across this whole area hit a single electron, and then the wave disappears and the electron takes all of that energy? You ever go to the beach? You ever get a boogie board and ride the waves? How strange would it be if the energy of that whole wave all of a sudden was absorbed into you and off you go? like into space. But if you're thinking about light as a wave, this is hard to think of this experiment with light as a wave. And so they say, clearly, we've solved it. Light's a particle. Okay. And so, and Newton thought light was a particle. So now you have Einstein and Newton both thinking that light is a particle. This is how our photomultipliers work. Our camera elements, to some degree, work a similar way. Light photon comes in, excites an electron to a conduction band, and you get a signal, and you turn that into an image. You can run it backwards. Electrons going into certain areas that when they have to jump a gap, they spit out a photon, and then you have displays and light-emitting diodes. So this photoelectric effect is light and electrons. And think about our society. All of those devices come from this effect. This introduced the idea of energy levels, and so we'll talk about that in this course. But what about waves? 100 years earlier, a pioneer looking at diffraction of light through a slit, Thomas Young, contradicted Newton, and his work was rejected just because he contradicted Newton. He was right to think of light as a wave and how it interacts and has constructive and destructive interference. And so this was what the comments were on his talk, that they were destitute of every species of merit, meaning they were worthless. So that's pretty sad. You could be too far ahead of your time and your work not be appreciated, so.
Don't want to hear that in your opinion.
No, you don't want to hear that. You finish your thesis defense and your advisor says, that was destitute of every species of merit. So these, I've shown some pictures of these folks. These are the Solvay conferences. And this fellow here, Ernst Solvay, was an industrialist, a philanthropist. He had an enormous estate, and he liked to be surrounded by smart people. And so he knew physics was a growing field. Think about it. This was in the early 1900s. We had nuclear power and nuclear discoveries happening. And so you had Rutherford there. You had folks like that. We had electronics and electrical, like electroplating and so on. So we had Debye, and earlier in this picture we had, right here, we had Nernst, so the Nernst equation. Nuclear energy, we had Marie Curie and Ernest Rutherford, and we have Einstein and De Broglie and all of these folks, and they would get together at this estate and have talks, and they would all on the chalkboard, no PowerPoint. Yeah.
Was Faraday before this?
I don't know. I have to look up where Faraday was. This is 1911. If anybody wants to look that up on their phone, someone Google Faraday and see when he was doing his work.
That's all I can remember.
Yeah. And so then this is the 1927 Solvay conference, and this now has the quantum mechanics folks in it. Heisenberg, Schrodinger. So here's Schrodinger, number one here. Heisenberg and others like Niels Bohr and Max Born, and so Einstein's here too. So is Curie. Pretty neat crowd. So this idea of spectroscopy, if you took hydrogen or any other gaseous element in a discharge tube, or maybe even a burner like a flame, and you have a little ring with some salty water in it. You ever do a flame test? You put a little like sodium or strontium or lithium, you put it in the Bunsen burner flame and it gives a color, like strontium will be like a purplish pink, or potassium. Well, you could take that emission, run it through a slit, run it through a prism, and put it on a photographic plate, and you would have the spectrum. And these lines on the plate were vertical lines because of the slit. Okay, and so they called these spectral lines. And we still call them that today. Even though we're not using photographic plates and slits, we still have slits in our spectrometers, but we have a detector, and instead of a photographic plate, we are having no signal and then some signal, and then no signal for a while, and then some signal. And so this is what our modern spectrum looks like. You see the signal go up and down, but we still call them spectral lines. Now, what's interesting is Bunsen invented the spectrometer, but the burner is what got his name. So the Bunsen burner, it was his spectrometer that he invented, but it's the burner that got his name. And the spectrometer is way cooler. but his little tube with hot gas in it, that's what he got his name put on. So you can't control what your name gets put on, apparently. Yeah. So this atomic emission spectra were quantized, and now we know that molecular spectra are quantized. And so that's really this course, is studying why these peaks are where they are. And so this was Bohr's attempt to understand why these spectra are quantized. He said maybe the electrons are in circular orbits like a solar system, and if light comes in, it pulls an electron from the nucleus. And then if the electron jumps back down closer to the nucleus, it can spit out light. So that's your photoelectric effect of electrons going closer and further from the nucleus. But this wouldn't work because of the charges on the electrons. They would spiral into the nucleus. So what keeps a discrete electron out of the nucleus is the question, right? Do you ever have that question? Right? Well, what got combined is this wave idea. So de Broglie was thinking about this and saying, what can have discrete energies? Music, a string on a violin or a guitar, right? You pluck the string and it has a standing wave. And what if I touch the middle of the string and pluck it? It has a different standing wave. It has higher frequencies, same length, same mass, higher quantized state. It goes up an octave. Okay. If I cut the string in half and make a higher, you could do a third too and get like the fifth. And so you could have a different wave. And so he was thinking about this violin string can have these standing waves, and they have certain frequencies, which is certain energies, and nothing in between for that string. Now, if you say, well, I can move my finger, well, you're changing the dimensions of the system. And naturally, you'll be able to get different frequencies if you change the dimension. Or if you change the tightness, okay, you're changing the spring constant, but it's still discrete standing waves. Okay, so you're changing the boundary conditions. You could change the mass and have a heavier spring. And so he was thinking about this and said, what if we applied this to the electron around the nucleus? He wrote that in his thesis. And then Einstein read the thesis, gave it to Schrodinger. Schrodinger said, if I use wave mechanics, and the mass of the electron and the potential of the nucleus, maybe I can solve the hydrogen atom spectrum. And it took him a couple of months. He did not know second order differential equations, so he reached out to a friend, and Hermann Weyl, and pulled him in to help him with the math. So even Schrodinger had to get help. And he solved the problem, and this is the top set of lines is the observed spectrum of hydrogen. Now this is hydrogen in an electric field because it's called the Stark effect, where it splits all of the little M sub L orbitals. In an electric field, they split apart and you have different intensities, and his theoretical matched pretty well. So he solved the hydrogen problem and he got his Nobel Prize. Okay, his work was much harder than Einstein doing a slope of a photoelectron. And so then he passed it on. Dirac picked his work up and pretty much finished it out. So Dirac and Schrodinger now have solved the idea of the electron around the nucleus. Now think about that. That's all of chemistry. Every chemical reaction, every kind of kinetic effect where the electrons are interacting with the electrons, it's all about the electrons because they're so far from the nucleus. If you can understand the electronic structure, then you can understand the chemistry. And that's what that software is called. The Gaussian software is really called electronic structure calculations. We're trying to get the structure of the electron cloud. And once we understand that, then we can understand the chemistry. So to give you an idea of how big an atom is, if this ball in front of target was a proton, so next time you're at target and you see that, think of the proton, okay? How big would the atom be? Hydrogen atom. How big do you think? See, extremely big. So I asked my kids this is what I do. You know, it's like, wow, look at that. What if that were a proton? Where would the atom be? And they were saying probably the parking lot, you know, the whole target parking lot, okay? No, it's on the map. You have to put it on the map. So it's 71 miles across. So that's where chemistry happens. 71 miles from here. Yeah, or 35 and a half miles from here. Yeah, right. So this is why we talk about valence electrons, right? The core electrons are irrelevant. The nucleus is irrelevant. Not completely, but mostly. 99% irrelevant. It's the valence electrons. They're the ones that are further out. Sodium. So sodium over here, row 3, the 3s electron, that single electron, how big is that? So if there's a sodium atom at target in Huntsville, and I'm coming onto the planet Earth, when will I find the 3s electron in Argentina? Right? So that's how far away that 3s electron is from the sodium nucleus. But it's attracted because look how many protons are in sodium. What is it, 11? That's a lot of charge. So it's still attracted to the sodium nucleus, but it's so far away it's easy to pull off. So if you can understand the electron cloud, you can understand the chemistry. And this course is using spectroscopy to understand the electron cloud. So we will learn about the software that calculates the shapes of the electron cloud, the orbitals, the molecular orbitals, and then also the spectroscopy related to those things. So these are the experiments that could not be explained by Newtonian physics. Blackbody radiation, the photoelectric effect, atomic and molecular spectra. And wave mechanics solved every one of those. It hadn't solved gravity yet, so there's still problems to be solved. We don't really understand gravity. The Higgs boson and the Higgs field is one possible theory, but we're still working on it. And quantum chemistry or quantum physics still doesn't really fit into Einstein's general theory of relativity. So there's still haven't figured out how those mesh together. So there's still work to be done. All right. So be encouraged. And I'll see you next time.
Isn't there a smaller particle in that? I can't remember what it's called though.
Yeah, when it gets down to that level, yeah, that's